ready.
Okay, you just have to make it a presentation view. All right. Well, good morning, everybody. This is Jomo Stewart here at the Fairbanks Economic Development Corporation. It is Tuesday, September 22nd, just a couple of minutes after 8 a.m. Here, 2020. And so our guest today here at the Energy for All Alaska Task Force meeting is Mr. Brent Sheets. Now, I came to know Mr. Brent Sheets when he was still over at Department of Energy. But for the last several years, he's been the director of the Petroleum Development Laboratory at the Institute of Northern Engineering at University of Alaska Fairbanks. And so, Mr. Sheets, if you wouldn't mind introducing yourself, the floor is yours.
All right. Well, I appreciate it, and I appreciate everybody getting up on a Tuesday. I'm kind of glad for the Zoom meetings because I can sleep in a whole half hour longer than driving downtown there. But I do miss seeing everybody in person. And the worst part of it, of course, is I can't tell if any of the jokes that I usually say work because I can't see any of you. But I'll just assume they don't, so I'll stay away from the jokes today. So I'm going to talk about 4 projects today, and the theme here is just what we're doing to support the Alaska economy, because it seems like it's very one of the missions of the university seems to me that it should be to support the economy of those that pay our bills, and we take a lot of taxpayer money, which I'm very grateful for. So I'm also grateful for the opportunity to provide some of that back in the form of services to the industry that keeps us all well funded. So I'm going to talk about 4 projects today. I'm going to try to, I'm just going to give you like the fly overview of all of them. Try not to spend more than 10 minutes on any one of them. But the 4 that we're going to talk about today is a polymer flood project on the North Slope, a new carbon capture and utilization project that we're just spinning up right now. Kind of a catch up on our syngas project. As most of you know, we're doing a small scale coal gasification project to generate heat and power, and it was originally aimed at wind regulation, and we're still providing wind regulation in our plans. We have not negotiated anything formally with Golden Valley yet. And then we're just at the very stages of getting ready to apply to a funding opportunity that we know Department of Energy is going to be issuing soon on rare earth elements. And so we're at the team building stage on that. So we'll just spend a little bit of time on each one of those. First, before we get into the enhanced oil recovery projects, I thought I'd give us a little bit of a primer on the oils of the North Slope. Generally, we talk about 3 different types of oil: a light oil, a viscous oil, and a heavy oil, and they're all at varying depths of the underneath the infrastructure there, subsurface depth. Most of the Prudhoe Bay stuff that we're doing, the light oil, it's green. That's, as you can see, mostly developed. That's anywhere from about 12,000 feet up to about 5,000 feet. But then you get to a shallower depth, i.e., closer to the permafrost, and you get into like the viscous oils, which are as we say here, more like a pancake syrup. Right now, they're developing. It's very slow to develop because we don't have a lot of the technologies to develop them. And then ultimately, there's these other types of oil, the heavy oil, that we don't currently have any technology to be developing at all right now. So going back to the developing, this is the area where we are focusing right now. This is a viscous oil. Like I said, it's like pancake syrup. If you were in the lower 48, this would be an economic play to go after. You would just put a lot of hot water, a lot of steam down into the reservoir and heat it up. But because we're so close to the permafrost, that's really hard to do. And I'll give an example of that in a little bit. But why are we focusing on it? Because there's like 20+ billion barrels of this heavy viscous oil just waiting for that technology to be there. So that's where we're focused. That's where a lot of the working interest owners are starting to focus. One of the reasons that it's such an attractive play is that in most of our developed infrastructure on the North Slope, you drill right through that West Sac, Schrader Bluff type oil on your way down to light oils. So it's a target that you could largely get without increasing the footprint on the North Slope. So that's why we're working on non-thermal technologies to develop it. Another way you could get it is to put in a bunch of solvents. Yeah, sorry, was there a question?
No, but if I may, actually, yes, I had a question. So this is JOMO. Is that viscosity, is that a function of temperature mostly, or is it really something intrinsic to the oil itself? Because I do notice that, again, it seems to get thicker as you get closer to the surface and cooler.
Yeah, it's mostly intrinsic to the oil itself, but it's exacerbated by temperature. So think of your maple syrup, your pancake syrup, at room temperature, it's going to be better than it is in the refrigerator, but it's still thick. It's intrinsic to the nature of it. So we're used to talking in terms of API gravities, like the API gravity in your engine oil would be, you know, on the 30-ish side. You know, that's, so if you're familiar with your engine oil, you pour that out. The viscosity of like a pancake syrup would be something like a 15 API gravity. So it has to deal with the specific gravity of the fluids and its makeup. Usually through the heavier oils have lost their light ends, which is what makes them heavy.
Ah, okay. So we do have another question. Can existing wells be used to access the viscous oil, or would new ones be required?
That's a good question. I can't answer that because I'm not that technical, but I would suspect that you could place a few packers in there and access that viscous oil. The thing is, if you don't design your well initially to do that, it's a little bit harder because you don't want to inadvertently start mixing zones. So you have to have a wide annulus and put down a few different, you'd use a slightly different technology with that in mind. You design the well with that in mind in the first place. So I can't answer that because I don't really know how those wells up there are designed.
Okay, thank you.
But you could use the same gravel pads. That was my point. You could use the same gravel pads, the same roads, the same pipelines, even if you have to drill new wells.
You just may need to use different, you know, purpose-built subsurface infrastructure.
Yes.
Okay.
Okay, and then that's just kind of the primer of heavy oil overall. I wanted to just kind of get a little bit into the polymer flood project. This is a $10+ million project that we're working on with primarily Hilcorp, and it's funded by the Department of Energy. The location of it is the Milne Point unit, which is about 30 miles to the northwest of Prudhoe Bay. It was a 50-50 split between Hilcorp and BP, and now, of course, it's all Hilcorp owned. And they have been fabulous partners to work with. I'll get a little bit into the polymer itself in just a second, but basically how this works is the polymer is manufactured in the Gulf Coast area of the United States as a powder. It's shipped up to Alaska, as you might guess, at great expense. It is then mixed with water until you get a certain viscosity, and then it's injected into the injection wells. There's not a lot of infrastructure to make it work and to make it happen. So for those of you that really aren't familiar with oil field operations, you have an injection well, and then some distance away you have a production well where the oil and fluids come out. In the injection wells, you're usually placing a gas, a miscible injectant, water, and you're pushing that oil away from the injection well and towards the production well. Typically, since we can only use non-thermal means on the North Slope, we use a lot of water up there. And again, going back to just thinking about your pancake syrup, when you have that plate, especially you have a little kid with lots of pancake syrup left over and you run water across that plate in your sink, you see those little channels of water, those little fingers of water that kind of get through, they break through those areas, and then maybe have another finger break through someplace else. And then over time, you know, it comes back and gets all that viscous product from between them. So you can imagine in an oil field operation, if you're putting this water under a lot of pressure in there and you get a finger that pokes all the way through to the production well, you're getting an awful lot of produced water relative to the amount of oil that you're getting. So with the polymer flood, that kind of takes away this fingering attribute, and it's more like putting a snow blade on the front of that water blade. So now it's just a whole lot more efficient at pushing the oil towards the production well. So that's one of the reasons that you would use polymer. Nobody's ever used this before in a heavy oil production, with a few exceptions, I think in Russia and maybe in Canada. This is a really busy slide, and I apologize for that. Hillcorp presented it on Friday. I loved it. I asked for a little easier version to read. I didn't receive it yesterday. I'll probably have it today when we're done with today's meeting. But I just want to spend a little bit of time. Yeah.
Two things. First of all, we're still on the viscosity slide. Visually, okay, so that's just flipped. Thank you. We did have a question though on the last slide. Why couldn't hot water or steam be used to push the oil like they do in the Canadian oil sands? Or was that really what you were describing? Again, the fingering, the fact that it'll punch through.
You can't use the hot water or steam because you're going through, your injection well is going through 3,000 feet of permafrost. And permafrost doesn't have any mechanical strength in and of itself. And if you start to melt it, it turns into like tapioca pudding. And it essentially, the well essentially separates from the surrounding permafrost. And the weight, you can imagine a 3,000 foot straw vertical, it can't, the bottom part of that well can't support the weight, and you end up getting that well buckled. It kind of turns into a spring, if you will. There's a deviation, and it just couldn't handle the weight. The other thing that you could do is, of course, you can insulate around the hot water or steam injection well, but eventually that insulation is going to come to equilibrium to its surroundings. So you're still going to, after X number of years, start to melt the permafrost that's around the well. So insulation isn't going to work. So that leaves you with some sort of an active cooling mechanism. You know, you'd have one well, you know, you'd have a well pumping hot water or steam down, and then you'd have an outside water jacket or a glycol jacket that's for cooling. But you can imagine the amount of energy that that's going to take on the North Slope to have an outside water jacket circulating a cooling fluid through there. So you're burning a lot of natural gas or using a lot of energy to generate the hot water and the steam, and you're using probably that much or more energy to create that cooling jacket, and then you've got all the pumps and everything that you're running with it. So that's why typically it's just not thought to be a wise idea or even economical to be using hot water. The other thing is, kind of on a little bit of a soapbox here, if you separate the well, what doesn't matter if it's a production well or an injection well, from that surrounding permafrost, now you've created a channel for natural gas or other dangerous fluids to come to the surface, and you have no way to control that once it gets up there. So it's very important to maintain the integrity of the wells as it's passing through that permafrost. Does that answer the question?
Yes, I think so. Oh, okay. Thank you very much.
Are you on to the very busy slide?
Yes, sir.
Okay. So can you, I don't know if you, can you see my cursor when I move it?
Yes.
Okay, thank you. The two colors on this very busy slide that I want to draw your attention to are the green dots and lines, and I don't know why there's dots and lines, but the green represents oil production, okay? The blue represents water production. So you can see that in late August, early September of 2018, when the polymer started, you can see that the water production was considerably higher than the oil production. After about 3 months of injecting the polymer, you can see that the oil production is starting to rise and the water production is starting to go down. Now, here we are, almost 2 years later. This is just a little period where the well was down for some maintenance issues. But when you move on past that, you can see that your water production continues down, and it's virtually zero right now. and your oil production is trending upward, and overall you have a whole lot less fluid coming to the surface that you have to deal with. So when you have a producing well and you bring all that water up to the surface, you have to treat that water, clean it up, inject it. There's a lot of expenses associated with dealing with that water. So the less water you produce, the lower your cleanup costs. And of course, the more oil you produce, the more revenue that you generate. So you can see that the injection of polymer has been very efficient at reducing water. It is doing a lot better. It's being a lot more efficient at producing the oil for the amount of water that you are using. And overall, your costs are lowering, so your profits are higher. And it's that sort of thing that's going to make this viscous oil development profitable and possible in the future. We're already seeing some companies on the North Slope have a huge interest in adopting this technology. A few of them, we're hearing anecdotally, have started their own injection projects. And I believe Hillcorp has plans to move this beyond the Milne Point unit and into the Prudhoe Bay. And every time I talk to Hillcorp, they tell me that my next task is to figure out how to manufacture this polymer in Alaska. So if anybody wants to jump on board in that project with me, let me know. I've started a few inquiries. I don't know if we'll ever be able to fully manufacture it here, but sure be nice. So that's our kind of our flagship project on the North Slope right now. Department of Energy is very proud of it, and they're publicizing it very greatly. And those are our partners. You know, I could take the BP slide off there now, but they've been so instrumental in getting it started. They've been very supportive of the Petroleum Development Lab overall. And then we're working with New Mexico Tech and University of North Dakota and Missouri. Yeah.
Okay, so do you mind hopping back to the last slide? We have a couple of questions. So from the chat box, can the produced water be cleaned and then reused, mixed with more polymer?
Yes. Yeah.
Okay.
In fact, and typically the produced water is cleaned and reused and recirculated through the wells. Yes. I will say this though, now that the water, we haven't had any polymer breakthrough yet. So we monitor the produced water. We're looking for polymer. After 2 years of injection, we still haven't detected any trace amounts of the polymer. But when that polymer does come through, it is going to complicate the water processing. So one of our other projects that I'm not talking about today is how to separate that polymer out of that water. But anyway, yes.
Okay. Is the volume of polymer input dropping slightly too? I guess the amount required.
Yes, the volume of polymer has dropped considerably. So the way that we work this is that we run a lot of different models in our lab, including, you know, taking sand packs and running oil and polymer fluid through it. And initially, that's how we sort of set up our ratio of polymer to water to everything else. What we have done over the last 2 years is the amount of polymer, I don't remember what we started with 2 years ago, but basically we're using about 2 pounds of polymer for every incremental barrel of oil that we're producing. So for every 2 pounds of polymer, you get an additional barrel of oil that we didn't have before. I'm not even going to hazard a guess as to what we started with, but that's significantly less polymer than we were using 2 years ago. And the other thing that we're finding is that we can inject at a lot lower pressure than what we've been using before and still get the same results. So we're cutting costs that way too. You don't want to overpressurize a reservoir because these are all unconsolidated sands and you inadvertently make new pathways for the oil and the water and communications that you don't want. So the lower that we can make the pressure, the better. So, yep.
Okay. And what is required to make the polymer in Alaska, or would be?
Well, I actually have a paper that I keep on my desk that has all those ingredients in it, but that paper is at the university and I'm calling in from home, so I can't remember everything that there is. I'll just tell you results of my initial investigations, and I've taken 2 different stabs at it. I'm looking at using North Slope natural gas as one of the primary ingredients. I'm looking at all the constituents in the TAPS oil as some of the constituents, and we get about 1/3 of the way there. Some of the more advanced chemicals I need to import from the lower 48. So I'm very eager to see that railroad occur. But until that does, it doesn't look like it's any cheaper to import the feedstock to make the polymer than it is to just bring the polymer in. So it's still the most economical thing is to bring the polymer in. The other thing that it would take is essentially a refinery. You need a chemical manufacturing plant. It's probably $1 billion investment is my guess. So until this really takes off on the North Slope, there's probably not an incentive to even invest in the capital. But right now, we're still trying to figure out a source for all the feedstocks to see if we can throw it together. After 2 stabs at it, I'm not all that optimistic, but you never know.
Okay. And I guess this is a personal question. If I were to run this graph off to the left, would we be finding, overall, are we having an increase in production using the polymer? Because it almost looks like if you take the extreme left against the extreme right, they're about equal.
Yeah, they are about equal. I'd have to go back to Hilcorp and have them explain the dramatic variation at the very beginning and what's to the left. I honestly don't know what's to the left of where the polymer starts. The oil production there probably was going up because Hilcorp had been investing a lot in the infrastructure there before they invested in the polymer. So there's a whole change in operations, as you can imagine, after Hilcorp took over from BP, and you did see an initial spike in production, and that was just because of the maintenance type things that they were doing over BP. Since BP kind of knew they were going to be selling this field, I'm projecting here. This is not an official BP or Hilcorp assessment, but I used to run an oil field that was on its last legs, and you really don't make investments in it when you know you're going to close it down or sell it. So I imagine BP wasn't investing in it, and once Hilcorp became the operator, they just changed a few bells and whistles and upgraded a few things, and they saw a kick in oil production. So I imagine that that's what that kind of upward tick is just at the beginning of the polymer, and then things would settle down, of course, after that.
But again, if what we really are getting is equal production with a lot less input costs and less water, that's still a good thing.
Exactly. Yeah,
Okay.
still a good thing. And the polymer and the, just the changes in the operation, even with the introduction of polymer, is still cheaper than, all those huge amounts. I mean, you went from basically 50,000 barrels of water a day that you had to deal with to 0. Like a couple of weeks ago, we couldn't even get water samples up there. And here's kind of the fun thing, if you like problems. This polymer flood is working beyond anybody's models, beyond anybody's expectations, and we don't really have a theory as to why it's exceeding our expectations of operations. So if you're going to have problems, those are the kind of problems you want to have. Like, why is it working so well? Yeah. There's been a lot of papers that came out on this. This project is really putting UAF on the map in terms of polymer. I think we are becoming recognized as some of the nation's experts on polymer flood here because of this project. And we couldn't have done any of it without Hilcorp and without NETL, DOE. But it's us kind of pounding the pavement, going to industry. Just another sidetrack. I've been PDL director now for almost 3 years. And when I came on board the university, every 2 weeks I get a pink slip. And then it was like, oh no, we got enough money, you can stick around another 2 weeks. So another 2 weeks would go by and I get a pink slip. So I started writing a strategic plan for all the petroleum engineers who were going to be left behind if I ever had to leave. And I realized, this is really stupid. I can't write a strategic plan for the oil industry. So I just started going to Conoco and BP and Hilcorp and a few others, because that's when there's a lot of explorers going on in the North Slope. I said, you know, guys, you've worked all over the world. You've worked all over the country. They've had universities every place you've worked. What have those universities given you that maybe UAF isn't giving you but should? And I really need you, the industry, to write UAF into your strategic plans. I don't need PDL to write a strategic plan. I need you guys as the industry to write us into your strategic plans. And that really resonated with them, because I don't think a lot of people have approached them with that sort of mindset. So we get a couple of inquiries a year. I mean, it's still, nobody's breaking down our door. Can you do such and such in your lab? And that's actually how this polymer flood project started a long time ago, before I even got to PDL. Hillcorp came to the university and said, you know, we're really interested in this. What can you do in your lab? And there was no DOE funding at that point. It was all Hillcorp. And we have another project that, you know, we're working towards that's right now 100% industry funded, but it's not ready for prime time yet. So, I mean, those are the sorts of things that I'd like to see Petroleum Development Lab kind of get away from a lot of taxpayer funding. I mean, if we're really going to be providing the industry with anything, then the industry should recognize that value and help carry the cost. That's how I'm looking at it. So we're just trying to provide a service. So.
Okay. I do have one last question really regarding the polymer, and that is, what is the downside, or have we identified any, if the polymer cannot be recovered later?
Well, this is the first time polymer has been used in viscous oils. Polymer is widely used in light oils. So we have every confidence that we'll be able to recover it. It's really kind of the test that we're having is what solvents do we need to work on this specific water chemistry that we have. And then there's just a few other minor things that you got to tweak in the field. For example, if you have to heat the water beyond a certain temperature, I don't remember what it is, I want to say it's like 160 degrees. So if your water is more than that, that polymer will start coating the walls of your heat exchanger, turns it into like a little Teflon pan. So then you start getting that insulation on your heat exchanger, and your heat exchanger becomes less efficient. So those are the sorts of things that we're kind of fine tuning and playing with right now.
Okay.
Yep. So this is another North Slope project, carbon capture and utilization for EOR. And it really started, this one was even started by BP a long time ago. They said, you know, Brent, when we get permission to build the gas pipeline, that tells you how long ago this was, you know, we're going to have to separate out the CO2 from that natural gas. And the general thinking in the oil fields is you put that CO2 down into the oil reservoir. It is an amazing injectant for additional incremental oil production. It works great. Typically, you don't exceed 20% CO2 in a reservoir because it can become corrosive when it comes into contact with water and perhaps some other fluids. And BP's concern, now this was years ago, was that we have way more CO2 than we can possibly put down into the well. So help us come up with a North Slope carbon management plan. What can we do? Because we're BP and we don't want to be seen venting all that CO2 into the atmosphere. So we kind of noodled it around a little bit, started with them. And then, you know, BP, of course, sold to Hillcorp. So that was, you know, less incentive to move on those things. Hillcorp was still getting their arms around operating the field. This was kind of a distraction, although they did offer support for the project because they too see the value of not emitting that much CO2 into the atmosphere, but it wasn't their highest priority at the time. So circle that back around. There's now $1 million opportunity that we were approached with by the University of North Dakota's Energy and Environmental Research Center, the EERC. So the EERC actually recruited us to join their team because of their history of CO2 EOR. EERC started in 2003 with funding from the Department of Energy to just look at characterization of CO2. They got another award that carried them through 2008 and another award that carried them through 2019. And over this time, they worked with the Dakota coal gasification plant, which was the first ever commercial sized coal gasification plant in the United States, to separate CO2. They built like a 400-mile pipeline to take it to the Weyburn field where they inject it into oil. It's probably the most well-characterized oil field anywhere for assessing what CO2 does. And since then, they've had a few other successes working with coal-fired generation to separate out the CO2 and to inject it into EOR and a few other areas. So at the urging of Senator Murkowski in the Energy Committee, because the Senator of North Dakota is on that committee too, they said, well, what can you guys do in Alaska? So PCOR called us, which stands for the Plains CO2 Reduction Partnership. You can see that their original area was this yellow line around the map. And they added British Columbia, parts of Wyoming, and now they added Alaska to the group. It's a big partnership, well-funded. They get their results out into industry, as you can see here. The group at the top are the principal players right now in this version of the PCOR thing. We again went back to Hilcorp, and it was BP still at the time when we received this $1 million. We worked with the industry to come up with a scope of work, and there's two tasks. One is evaluate the incremental oil production from a North Slope field by initiating a high concentration of CO2 EOR. So right now, in much of Prudhoe Bay, so right now, in the Prudhoe Bay, they're using what's called a Prudhoe Bay miscible injectant, and I don't have my note screens up here, but it's 20% CO2, it's like 30% methane, it's a number of light ends that you put in there as a solvent. And then that collects some of the oil off the sands, the rocks, and then it is produced as oil. So we're looking at high concentration CO2, 60% perhaps higher of CO2 that you would inject. And again, we're aiming, Hilcorp asked us to look at the Orion field, which is right smack in the Schrader Bluff, West Sac area. Again, it's in Prudhoe Bay, the Orion and the Polaris fields. What we're doing is we're examining, we're creating a few models of their fields. We're getting data from them shortly where we can be setting up reservoir models. We can see what the amount of incremental oil is for the amount of CO2 that we inject. But the real meat of this is task number 2, which we will begin probably in January or February, maybe the spring, which is to evaluate the implications of using CO2 in an older field, especially the effectiveness of corrosion inhibitors in the presence of high concentrations of CO2. So you can imagine corrosion is a big issue up on the North Slope. When you deliver dry CO2, you really have no problems. But once you inject it into the reservoir and you start producing it, now it becomes an acid. And if you haven't designed your field to be inoculated, if you will, from some of those harsher chemicals, then places like valves or seals, you start to have a few issues with those. So, one of the questions is, well, how many valves need to be replaced? How well does the CO2 work in the presence of the corrosion inhibitors that they're currently using in those pipes? So those are just a few questions. And this is really right now at this point an academic study because there is no natural gas sales to the lower 48 at this time. So we don't have the types and the quantities of CO2 that we're talking about to get there. But what we're doing is we're laying the groundwork. We're creating publicly accessible data about what the effect of CO2 usage on the North Slope is going to be. I think everybody agrees it's a good idea because when you use CO2 for EOR, some of that, a good chunk of that CO2 remains behind in the reservoir permanently sequestered. So we're trying to get our arms around, well, how much CO2 is continuing to circulate, how much CO2 is left behind, what are the effects on the fields, what's it going to cost, what's the upside potential, what's the downside risk. Those are the sorts of things that we're looking at. And we're just, as I said, trying to create a public record. It's an academic exercise of modeling, working very closely with the industry, and we'll see where that path takes us. We'll be doing that for the next 2 or 3 years, funding a number of grad students. And we're working, as I said, very closely with the EERC on that.
Jim will correct me if I don't speak for him as well. But kind of giddy that you're actually looking at this. You know, we looked at a coal, excuse me, biomass to liquids project some years ago. It was going to make, as you would expect, high quantities of pharmaceutical grade CO, and we wanted to possibly use that on the North Slope, or have it looked at. So we're glad that that's moving forward.
Mm-hmm. Yeah.
So he hasn't yelled at me, so I guess I did speak for him. Let's see. What kind of acids are formed from CO2? I think carbonic acid is one. Is that correct? I mean, that's soda pop.
Yeah, well, yeah, that's the primary one. Again, I don't have my speaker notes up. I don't know what happened to them on the screen. I had a few of those derivatives of what happens when you mix those together. I don't feel comfortable saying from memory because I'm just not technical in that area. So,
it's okay, but I think I remember
I could take some guesses, but I'd be wrong. And since this is recorded and on YouTube, I got to be careful. What was Jim going to say?
Nothing. He's just throwing me dirty looks. I can't believe we don't have any more questions on carbon sequestration, but just know, everybody, I am monitoring the chat box. And if you do have questions, you can take yourself off and we'll have time at the end. Okay, so small scale coal gasification, please.
Yeah, so this is a project that we've actually been working on for about 3 years. We've spent almost $3 million on it so far, designing it, and the feasibility of it looks really, really quite promising. It's part of a competition. Phase 1 was to do a kind of a technical assessment and a front-end engineering design, which we've accomplished. It's a competition sponsored by the Department of Energy. There were maybe 15 teams that were awarded the initial opportunity to be looking at their projects and pitch them. Phase 2 was a down select. They selected 5 teams from around the country to proceed, and that's where we're at. For Phase 2, we need to complete our environmental permitting, which we're in the process of, and we hope to get our permits submitted to the DEC by the end of December. The clock is ticking, and I tell you, we're a little bit behind the 8 ball on that. But if we miss any of the deadlines, we're out of the competition. So we have tremendous incentive to get our air permits submitted. We have to raise cost share for construction. This is going to be an $85 million project. We have to come up with roughly $16 to $20 million in cost share. I think we've kind of accomplished that. So we should be pretty good there. We need to update our design because we did change site locations. So we've got a little bit of doing. But the whole goal here is to demonstrate small scale coal gasification to fuel a reciprocating engine generator to make electricity and heat. We want to make it small. It needs to provide for load following services, meaning it ramps up and ramps down. The genesis of this project was to provide Golden Valley with an option or an alternative to using their North Pole power plant for wind regulation. I won't get anything into the wind regulation in this presentation, but I saw we had Steve on the phone earlier. He could speak to that as well. Ideal for islanding systems, meaning that we could put it on the military base, for example, and if the Golden Valley grid ever went down or the base had to be separated for some reason, it could still operate. And then it's just good for local jobs. Here's kind of a listing of the equipment. This is what a gasifier looks like. This is a prototype that was built by, well, it was designed by HMI and built at the Sotocarbo labs in Italy. We are partnered, or Sotocarbo is partnered with us on our project so we can glean all their information from operating that gasifier. It makes a low BTU syngas, and that low BTU syngas goes into an engine that's designed for low BTU gases, the Jenbacher engine, which was formerly owned by GE. A company called Ineo just bought it here within the last year. You would typically find these Jenbacher machines on landfills where they burn landfill gas. There's like 2 or 3 of them down in Anchorage, as a matter of fact. And there are distributors and support networks here in Alaska. We're very familiar with the Jenbacher. The other component is that this gasifier makes tars and oils, liquids, if you will. And our plan is to blend those tars and oil liquids with ultra-low sulfur diesel or equivalent, and then burn in a diesel engine. This was the university's peel stick 9.5 megawatt engine, but about 2 weeks ago we decided to not use the university's engine, and we're going to put a Wärtsilä in there instead. I'll have to update my spreadsheets. So this is just kind of a little bit of a walkthrough so that you can sort of better visualize what we're trying to do. So coal goes into the gasifier, a synthetic gas comes out and it gets cleaned up in a cyclone. Okay, then it goes through a cooler, because if you send the hot gases into our ESP, electrostatic precipitator, you burn it up. So it goes through a cooling phase. Then that syngas goes through the wet electric static precipitator, and that's essentially where all the tars and oils mixed with some water drop out. And we're working with companies right now to separate the tars and oils from that water and to clean up the water for reuse. Our plan is actually to use it as irrigation for 10 acres of greenhouses. Then that gas gets cleaned up to take out any of the other remaining nasties, including all the sulfurs, and it goes into the Jenbacher engines where it makes electricity and heat. What I didn't put on this chart is then you have a stream here, blends with the diesel, and goes to the diesel generators. Our hope is that Golden Valley will work with us and use the diesel generators for their wind regulation. So the DOE goals are that they want small units, and what I laugh at is they define small as 50 to 350 megawatts. Our project is 18 megawatts, and we actually have 3 different options. That's the largest of our options. Ultimately, we want to modularize this system. We want to get it up. We want to develop the technology. We want to prove it. Then we want to be able to put it on skids, you know, build them in some central manufactured area, ship them out to villages where they might be able to use them with the existing diesel infrastructure that's there, ship them to third world countries where they might need more reliable power, or even ship them to the lower 48 for a few applications there. We're building this in a serious non-attainment area for PM 2.5, and even with throwing all the bells and emission controls, everything at it, in our market, it still should be economical. It should come in. Our models are all showing that with even meeting all the stringent PM 2.5, we can generate electricity for about 10 cents a kilowatt hour, which you know, is expensive for the lower 48, but for up here, that's a pretty good price. Of course, we're going to clean up the water. Our goal is for greenhouse use irrigation. Capable of natural gas co-firing, so if our syngas unit ever goes out or the project just goes belly up, those Jenbachers can be repurposed and used anywhere. They'll fire on natural gas as well as on syngas. Capable of high ramp rates, so we can use them for wind regulation if that becomes an option, and then of course it generates all those tars. And we have designed it to burn 20% biomass, but kind of an interesting part about that is that we can't get our arms around permitting a combination of coal and biomass. So we put biomass on the back burner. Our goal is to get this thing up running 100% on coal, get some good baselines going. It is, after all, a research project, and then work with the regulators so that we can introduce biomass. Originally, this project was going to be at the university. We spent about $1.5 million redesigning the Atkinson plant to take it. Then there was a change in management there, and they said, we don't like your toys in our facility, move on. So much to the chagrin of DOE, after spending $1.5 million, we had to find a new place. So we started looking at co-locating it with Healy 1 and Healy 2. Got about 2 weeks down the road on that, and then there were a lot of management changes at Golden Valley, and the new management would prefer that we moved on elsewhere because this wasn't consistent with the Golden Valley's board of, I believe their strategy for meeting their CO2 reduction target is to reduce the amount of coal. I think there's other ways they could do it, but I think in the minds of some of the folks there, CO2 reduction is synonymous with reducing coal. So they asked us to find a new place. We looked at a few places in North Pole, and we ended up actually, because of our time constraints and because he's got everything we need, being on the site of Chena Power, where we have rail access, we have a power line, a three-phase power line directly into the Golden Valley system. We have room to build 10 acres of greenhouses. And I think FADC did a number of studies years ago on the need for local food production and greenhouse production. And I only know that because I used a lot of those reports as research for this project. So kudos to FADC for forward thinking. Again, for this particular option, we're looking at is there a question?
There are several comments in the comment box, but why don't you continue?
Okay. Very quickly, this is a chart that compares our syngas project against what Golden Valley is using for their diesel generation versus what we can maybe do with natural gas here. We didn't spend a lot of time fleshing out the natural gas because you didn't have the storage at the time, so it really wasn't an option for power generation for us. Our fuel costs are going to be about $76 a megawatt hour, $10 an MMBTU, versus what diesel Golden Valley is using. Now, this is just the liquid fuels costs of Golden Valley. This does not include the coal costs, only the liquid fuels costs. So they're generating power and wind regulation for about $15 an MMBTU using liquid fuels. We're designing our system to regulate about 10 megawatts of wind. If Golden Valley wants more regulation, this number is very easy to change because we haven't settled on our Wärtsilä yet to replace the university generator. The university capped us at 10 megawatts. The Wärtsilä gives us whatever we need. So I really haven't sat down with Golden Valley to see if they're wanting to go higher, and I can't speak for Golden Valley, but they have not entered a power purchase agreement for us. This is all speculative on our part, but they know about our project. I'm in regular communication with them. So our fuel cost for regulating 10 megawatts of wind is 3.1, whereas the Golden Valley's attributable share for 10 megawatts is $6.5 million. So you can see that we're like half that cost. So if we can go higher, maybe there's more savings to be had. This is just the total generation capacities of all the systems. So this is the biggest challenge we face, is getting this permitted in the Fairbanks Serious Non-Attainment Area. So those are some of the hurdles that we've identified. I actually have another meeting at 10 o'clock today to kind of get updates on all that. Why are we doing this? Well, for one thing, it lowers the cost to interior ratepayers. But our goal, remember, is to make this really small and modularize it. There's 37 villages sitting on top of coal, and those that don't even have coal, they're on the river systems for the most part, and they're already receiving diesel by barge. I make the argument that coal is actually the environmentally friendly choice for these villages, because most of these villages are reliant on those rivers for their food source, their fish and everything else. If you have an oil spill in those rivers, or if one of the tanks that they store near the river should spring a leak, you have irreparable damage. I shouldn't say irreparable, but it'll take the rivers a lot of time to recover. If you have coal and it sinks, the fish swim out of the way, right? So there's a lot of opportunities. And if you are also developing the coal in your villages, that's jobs in your villages. You're not sending that money to some refinery in Seattle. Now, can it work? I mean, At 18 megawatts, we're still looking at 10 cents a kilowatt hour. Now that's expensive for the lower 48. That's reasonable for Fairbanks. That's a bargain for the villages, but we can't really make it work at 2 megawatts yet. There's just too much capital involved. There's a whole lot there. So our goal is to view this as a research facility. We want to work towards getting it down to a village scale. We also want it to be really easy to integrate with the diesel infrastructure that's there. Most diesel engines, you just put another nozzle on them if they're newer and start burning natural gas. You don't have to burn diesel fuel in them. And then even if you do have to, we've got the liquids and tars that could be heating oil in homes or whatever. Could be blended with diesel, so it stretches your diesel. There's a lot of uses for this. But we're still, like I said before, we're not ready for prime time with that. This is an ongoing research project. So really what we're building is a demonstration project that's going to be a research facility. And ultimately, we want to get it where we can use biomass, and we want to ultimately get where we don't even have a smokestack. Another reason that the DOE picked up on and why they funded this project is it's useful in the lower 48 too. There's a bunch of aging coal-fired plants down in the lower 48 that are on their last legs. They're getting their butts beat by natural gas because there's more renewable energy going onto the grid system, intermittent resources. Just look at California. The sun goes down, the solar goes away, the wind blows some days, it doesn't blow the others. Natural gas is available 24/7 to sort of fill that void. It's there. Coal plants are just too big and lumbersome. They can't ramp up and down like the gas plants. But you take a system like the one we're designing, which is small and it is able to ramp up and down, and you put it at the interface of that coal plant with the grid, then a plant like ours takes all those hits from the intermittent up and down. They follow that wind regulation, while those big coal plants behind can take their time moving up and moving down. So we've got, I think, tremendous market potential once we get this technology developed. Now, except for the HMI gasifier, all the components that we're using are available commercially. They're generally skid mounted already. All we're doing is a new application and a new way to do it. And even the HMI gasifier is pretty well understood. There were some projects as a result of the Arab oil embargo in the 70s that I'm old enough I remember some of that. So I actually got I got in contact with one of the guys that ran one of the gasification projects from the 70s. So that's the technology we're using now. It's based on the Wellman-Galusha design. Doesn't mean anything to you guys, but there's 80 years of history running those things in steel mills and every place else. We're just modernizing it, instrumenting the heck out of it, bringing it up to modern times and modern performance standards. And emissions is going to be the key factor. NETL has come right alongside. They're excited by this. They're spending their own money to model this system. We understand its performance in the bed, the coal bed, that is, performance. That didn't come out very well. Anyway, it was going to be a lot of, there's a lot of excitement around the industry for this. The main thing is, can we meet all of our deadlines? I think if we meet our deadlines, this is going to be a very competitive project, and you're going to see a big investment in Alaska from the Department of Energy on that. Because of time, I'm going to stop there, but we're working with DGGS and a few others to put together a plan to go after another 50 million or so to start examining Alaska's potential for rare earth elements. And I'm going to stop talking, but I'll leave this screen up because I just want to point out that the blue lines here are all the rare earth elements that Alaska has the potential for. The green is what the rare earth elements that Alaska used to produce but aren't, except for one that's ramping up. So that's a lot. I'm going to stop there.
That's great. Okay, so we had a few comments regarding the gasification project. And again, I'll start with just Jim and I here at FEDC, just the fact that we're thrilled that you're getting this to the actual demonstration phase. Again, we did the original Hatch report, gotta be over a decade now. But we saw real potential in it, and so we're just thrilled that you're being able to move this forward. And so just so I'm clear.
On an aside though, we're not to the actual demonstration phase yet. We gotta win that phase 3.
You're getting further than we did, buddy. And we're thrilled. So let's see. Let's jump to Mr. Rowe's questions because they're direct. How does heat production compare with technology challenges and financial considerations for the coal gasification project? And George, you may have to hop on and ask that one direct.
Hi, Brent. This is George.
Hey, George.
Really excited about the possibilities of working out there at that Aurora site. I'm just kind of curious about the heat production. You know, like if we did that either in parallel or instead of power production, is that not possible to monetize?
Oh yeah, we're planning to use all the heat. That's a huge commodity, and the project actually won't be economical without selling the heat. So we have every intention of selling the heat. One of our first preferred sites actually was the Marathon site down in down in North Pole, NP, because we could connect to the city utility system there. North Pole burns a lot of heating oil to heat their city water, and this would have been a phenomenal addition down there, but I couldn't get Marathon to respond to our calls inquiring if we could have that site. That would have been ideal. We could have provided heat to the city water system. There's the pool there and the schools. There's 2 schools, pool, you know, it just would have been ideal. But I couldn't get a hold of the right people. And our clock is ticking.
Right.
You want to ask your further follow-up question, George, regarding U of Wyoming?
Yeah. So just in terms of collaboration space and partners that are deep in coal land, are you working with the University of Wyoming, like their integrated test center?
They are part of our P-Core process, and my understanding is they're handling the economic side of it. I'm actually going to have a lot better sense of what Wyoming is bringing to P-Core. We have a meeting with them tomorrow. So to be honest with you, I've been in the same room with Wyoming, but I don't know exactly what the scope of work is that they're doing under the P-Core project, but I find that out tomorrow. But my hunch is that it's the economics and regulatory side of it that they're looking at.
Great. Thanks, Brent. Great presentation.
Okay, we did have a comment from Dawn Utilities, simply noting that they actually run those engines down, own and operate those engines down in Anchorage, running off the landfill gas. And I believe that our own landfill has been thinking about something along those lines for some years.
I made it down to Anchorage for the commissioning of those Jan Bakkers when I was part of DOE a long time ago. So,
well, they've been running reliably ever since. They're not without their maintenance challenges, but it's a good setup.
Excellent.
We have a question from Steve.
So you
Hagginson.
recommend the Jan Bakker?
Good old Steve he was actually the chair when we did the original Fairbanks Strategic Energy Plan, out of which came or was discussed the natural gas trucking, Susitna Dam, the coal biomass natural gas to liquids project. And so he had quite a bit of familiarity with this on the front end. He's referencing a Wiley gas scrubber. Said it seemed to be a simpler design as far as the gas scrubbing, and you want to see if you checked in on that. Well, then again, it's we're 10 years advanced from that study.
Well, there was one other technology we looked at. I don't remember the name of the company offhand though. Partially why we went with Bellini is they work very closely with Soda Carbo and designed the systems that are attached to the Soda Carbo demonstration unit. So we have kind of a baseline, a good understanding of what the Bellini system is going to do. So, and we did, like I said, look at one other company. I couldn't tell you which company it was though, without going through my notes. That was a couple of years ago.
And did I hear right that you said that the site that you managed to secure is by 9 Mile?
Yeah, it's Chino Power. Yeah, 9 Mile site. So they've got 10 acres of gravel pads there. They've got a rail connection. They've got an unused coal handling system. There's a line, 3-phase line from Golden Valley running into there. I hadn't originally selected that site for a variety of reasons, but in the end, it turns out to be the perfect site for us. Yeah.
Well, and I know that their past plans align with some of your future plans, particularly regarding using waste heat for growing, greenhousing.
That's it. That's exactly why we ended up there. Bernie's already got the plans, the greenhouse plans built. I talked to Department of Energy about it, and they have agreed to allow, if Bernie and the others move forward with those greenhouses, the Department of Energy has agreed to allow those expenses to count towards our cost share. So that's going to develop a huge business, going to hopefully lower food costs. One of the things that we're working with the engine manufacturers on right now is treating the emissions so that we can pass all those emissions right through the greenhouse and grow the food in an elevated CO2 climate, because I saw some off the chart numbers as far as what that does in terms of your yield. So what we want to do is make sure though that greenhouse is going to be safe for humans to walk through in human habitation. So we are in the throes of negotiations right now with the engine manufacturers. That's partially why we're not so. That's partially why we have confidence that we're going to meet the PM 2.5 emissions. If we can already hit the PM 2.5, it's just an extra little leap to get it to where you can make it safe for greenhouse, sending it through the greenhouse. The problem we're getting is that the technology provider won't guarantee us that it's going to be safe to go through the greenhouse. So they will guarantee us that they can meet the PM 2.5 emissions. So that's a big issue with us when it comes to liabilities. So that's what that's what we've settled on, and we're exploring the idea of passing it through the greenhouses.
Is there any kind of credit regarding CO2 emissions by having it, physically sequestered with plants?
There are tax credits available for CO2 emissions that have been brought to my attention. I told our economic analysis person that's doing all that and brought it to my attention that I didn't want that built into the models, that I wanted this just to be economical without those tax credits, and that we would consider the tax credits bonus if we qualify for them. But I personally, just speaking for myself, I think it's a bad business strategy to build a business strategy around tax credits. It either makes sense or it doesn't make sense, and the tax credits are just to help you get over maybe the initial hurdle. But I really didn't want that reflected in any of our models.
No, I think that's a good conservative approach. Okay.
Yeah, and going with.
No, please, Mr. Sheets, can continue.
Oh, I was just going to say, going with the conservative approach in our economic modeling, we are assuming the worst case for everything. We've added contingencies to every part of the process, every component that we're designing into it. And then when we're all done, we've assigned another contingency to the overall package. So I feel I wanted to be very conservative. There's been too many projects where you start building them and then suddenly the price tag goes high. So I'm trying to guard against that. If anything, I want there to be pleasant surprises where the price goes low. So that's been our approach.
Well, Mr. Sheets, this has been an excellent presentation, and you are doing excellent work, you and your team. Mr. Dotson, I was going to open up. Are there any further or final questions? If there are, you can go ahead and take yourselves off mute. I saw some representatives online.
Hey, this is not the current representative, but Doug Isaacson, you've got so many projects. How do you keep on top of them all? What kind of task management or project management software do you use, or is it all spreadsheets?
No, I use project management. I use a Microsoft Project Manager.
Good to know. Thanks. Just an aside, very impressive presentation, and looking forward to seeing the results, especially for rural Alaska and the interior here. Exciting stuff.
Yeah, me too. I know that we can see results in Fairbanks if we get to phase 3, and I think to get it to the small size and send out to villages, I don't want to mislead anybody. That's going to be another 5 or 10 year lift after. But at least we'll have the place to work it, the facility to do it.
We'll keep it appraised of anything that you need help with, if we could rally support, especially also this greenhouse project. That's very exciting. So whatever you need, keep us appraised. Thanks.
I think we need to, you should keep this presentation handy. Brent, I feel like the university may be calling on you for one of the legislative hearings to remind them of all the good work going on at the university and that incredible return on investment.
Happy to help out.
Brent, this is Jim. This is excellent, excellent stuff. Jim was right on target when he says that this is the kind of information that we need out in the street, to support our university. It is going to be a huge part of our economic future. And thank you for, for suffering with the 2-week pink slip and getting on board and doing this. So, like I said, this is great stuff. Thank you.
My pleasure.
All right. Well, everybody, if there are no further questions, if you do have any, I can always forward them to Mr. Sheets, or you can reach out to him at the university. Just so everybody knows, heads up for next week, we will be having a meeting next Tuesday, 8 a.m. Our guests will be Cindy Heil of DEC, Department of Environmental Conservation, as well as Nick Zarnecki, to discuss the recent occurrences and updates regarding air quality and air quality regulation. So again, yes, there will be a meeting next week, and it will be air quality. All right, if there's nothing further, thanks again, everybody. Again, thank you very much, Mr. Sheets. Everybody have a great week, and we will see you next Tuesday. Bye, everybody.
Bye.